Here we have an interesting question on alternating current. This will involve almost all the concept of this chapter. So the question says, a series LCR circuit is connected to an AC voltage source when L is removed. When we remove this inductor and replace it with a simple wire, then the phase difference between the current and the voltage is pi by 3. Okay. If instead C is removed, the phase difference is again pi by 3 between current and the voltage. So the power factor of the circuit is, they are asking us to find the power factor of this circuit, and they use a term as phase difference. Now what is this power factor and phase difference? Let's talk about these terms for a while. We must understand them in order to understand the question. So here let's assume some current I is flowing. We can actually calculate what is the value of I if we can divide the voltage by the total impedance of the circuit Z. Then we will get what is I. What is Z? Z is the total impedance, and in order to calculate Z, we can take the help of a simple diagram. Now, we can draw R in x-axis. In y-axis, we have two things. One is the capacitive reactance Xc, and another is XL, the inductive reactance. Xc and XL, they point in the opposite direction. Okay, so we are taking Xc above the x-axis and XL below the x-axis. So this thing will give the result as Xc minus XL over here and then R over here. Wow. Now if you want to find what is Z, you have to take the resultant. So here we can see the resultant is coming to be Z. Okay. And now let's talk about the angle. This angle phi is very, very important. Why? Because phi is the phase difference between the current and the voltage. Phi is the phase difference between the current and the voltage. Okay? Okay. Now, let me talk about the value of cos phi. Cos of phi is our power factor. So, we have everything clear now. Cos phi is the power factor. We have to calculate this power factor for our given circuit. And how do we calculate phi? Well, actually, we can calculate tan phi and then we can get some idea about phi. So tan phi, as we can see from the diagram, it is Xc minus XL divided by R. Okay, so this is how we can get some idea about phi, and cos phi will give us the power factor. Now let's go and try to understand the question. In the question, they said they removed this inductor and they replaced it with a simple wire. Then the remaining circuit has the phase angle as pi by 3. As we can see from the diagram, tan of pi by 3. What is tan of pi by 3? You can say it is Xc divided by R. From this, we will obtain what is Xc in terms of R. It is R root 3. Tan of 60 degree is root 3. Okay, so we get Xc in terms of R. Now let's go and find what is XL in terms of R. So this time we remove the capacitor and we replace it with a simple wire. We only have resistance R and inductor L. So we can see tan of pi by 3. From this diagram, we can see tan of pi by 3 is giving us XL divided by R. And from this, we can calculate XL. XL is R root 3. Wow. We also knew that XC, which we have calculated earlier, was R root 3. And XL is also coming out to be R root 3. Well, exactly the same value. Wow. Now, let's go for the entire diagram. We have R, L, and C. Everything in this circuit. So, when we draw the diagram, we will draw XC over here. This was R root 3. And then we draw XL over here. XL was R root 3. And then we have R. Now, how do we calculate the total impedance of the circuit? Well, this thing cancels out this thing. And the total impedance is R. Yes. So, between Z and R, what is the angle? Between Z and R, what is the angle? It is 0. Oh. So phi is equals to 0. And what about the power factor? What is the power factor? Power factor is cos phi. Cos of 0 is nothing but 1. Congratulations, we got the power factor. Power factor came out to be 1. And we can mark option A as the right answer for our question. Here is an awesome question on modern physics. Question says, the energy required to break one bond in DNA is 10 raised to power minus 20 joules. This value in electron volt is nearly. So, what do we have? We have a DNA. Let's take a bond out of the DNA and let's break it. We break the bond. Wow. We required some energy. It was 10 raised to power minus 20 joules. Okay. What is the value of this energy when it is converted into electron volt? So what is this energy in electron volt? This is the question. How do we solve this question? Well, we can try to remember this important relationship that 1 electron volt is 1.6 into 10 raised to power minus 19 joules. So tiny energy. 1.6 into 10 raised to power minus 19 joules. Wow. How do we get this? Well, let's try to recall the definition of 1 electron volt. This is the magnitude of energy an electron suffers when it passes through a potential difference of 1 volt. So you can see this energy will be Q times delta V. Q is the charge on the electron, which is minus 1.6 into 10 raised to power minus 19 coulombs, and you know what is the potential difference. It was 1 volt. So you can calculate the magnitude of energy change of this electron. Now, once we have this relationship, we can write 1 joule as equal to 1 electron volt divided by 1.6 into 10 raised to power minus 19. Yes. So this is 1 joule. What about 10 raised to power minus 20 joule? So 10 raised to power minus 20 joule is this much in electron volt. All right. So we can see that it is coming out to be 1 divided by 16 electron volt. Yes. And this thing can be written as 0.06 electron volt. Okay. So now we have our answer, 0.06 electron volt. This is the amount of energy we require to break the bond in our DNA, and option A is the right answer for this question. Here is a nice question for us on nuclear physics. Question says, when a uranium isotope is bombarded with a neutron, it generates krypton. 3 neutrons and this is the question. So what is happening? There was some uranium isotope. 235 was the mass number and the charge number was 92. Alright. And this is bombarded with a neutron. Now we have a neutron. What is the mass number of neutron? 1. What is the charge number of neutron? 0. It does not have any charge. Now when we bombard this uranium isotope, we get something interesting. We get a krypton. The mass number is 89 and the charge number is 36. This is given. And then we get 3 neutrons. So 3 neutrons, 1, 0. 1 is the mass number, 0 is the charge number. Alright. And then we get some mysterious element. What is this mysterious element? This is the question. How do we find this mysterious element? Well, let's just determine the mass number A and the charge number Z of this mysterious element X. Now, how do we do that? Well, I will say the total mass number on the left hand side will be equal to total mass number on the right hand side. This means 235 plus 1. This is the total mass number on the left hand side. This is equal to 89 plus. What is the total mass number of 1 neutron? It is 1. But we have 3 neutrons over here. So we have 3. Yes. So 1 plus 1 plus 1. This is 3. And then for element X, we have A as the mass number. This will give us the value of A as 144. So we obtain A. Now let's talk about B. So we have the total charge number on left hand side. as the total charge number on the right hand side. 92 plus 0, this is equal to 36 plus 0 plus z. Okay, from this we get the value of z, which is 56. All right, all right. So what is our mysterious element? X is no longer mysterious. We know everything about X. The mass number is 144. The charge number is 56. So this is our element. And we can see option C, barium, is our element. Option C is the right answer for this question. Here is a question based on center of mass. Question says, two particles of mass 5 kg and 10 kg respectively are attached to two ends of a rigid rod of length 1 meter with negligible mass. So the mass of the rod is negligible. We have a massless rod and we attach two masses on the two ends of this rod. The center of mass of the system from the 5 kg particle is nearly at a distance of. So I will repeat what is the question asking us. Here we have a rod. Its length is given to be 1 meter. Now there is some center of mass of the rod, let's say over here. What is the distance of the center of mass from the 5 kg mass? This is the question. What is this value of x? Now we understand the question, but what formula can you apply to solve this question? This formula is crucial. What is the formula for calculating the location of center of mass? You would say the formula was XCM is equals to M1x1 plus M2x2 divided by M1 plus M2. Now let me tell you that if we take the origin at 5 kg mass itself, if we take the origin at 5 kg mass itself, what is the value of x1? What do you think is the value of x1? You would say it is 0. Why? Because the distance of 5 kg mass from the 5 kg mass is 0. Yes, so sweet. So you can mug up this formula. Whenever you want to find the location of center of mass from one particular mass, then you have to look at the other mass. You have to forget everything about the first mass. You have to look only at the other mass. Other mass is m2. The distance of the other mass from the first mass is x2. We have to divide this by the total mass of the system, which is m1 plus m2. All right. Now m2 is 10, x2 is 1, and m1 plus m2, the total mass of the system is 5 plus 10, which is 15. Yay! Now this thing is giving us 2 by 3, which is 0.67 meters. Yes! So we got the value of x in meters, and if we convert that into centimeter, that is 67 centimeter. All right. So we can go and mark option A as the right answer for this question. Let's have a look at this question based on light energy. So question says light with an average flux of 20 watt per centimeter square. This is the energy falling per unit area per unit time. So light with an average flux of 20 watt per centimeter square falls on a non-reflecting surface at normal incidence having the surface area of 20 centimeter square. So here we have an awesome surface. How awesome? Some light is falling on this surface perpendicular to the surface, and this surface is non-reflecting. That is, it will absorb the light. And the area of this surface is given in the question. It is 20 centimeter square. Okay? And then the energy received by the surface during the time span of 1 minute is. So in time span delta t is equals to 1 minute, or we can write it as 60 seconds. How much energy is absorbed by this surface? How much energy is absorbed by this surface? This is the question. Okay. Now the energy absorbed by the surface would be energy per unit area per unit time times the area of the surface times the time interval delta t. Note, no energy is reflected by this surface. Okay? Now, what is energy per unit area per unit time? It is given to be 20 watt per centimeter square. Yes. What is area? Area of this surface is 20 centimeter square. Great. What is the time interval? Time interval is 60 seconds. Let's multiply them. When we do the multiplication, we can see we are getting 24 times 10 raised to power 3 joules. Watt second is nothing but joules. Okay. So this is the energy absorbed by this surface or energy received by this surface. And we can mark option A, 24 into 10 raised to power 3 joules, as the right answer for our question. Let's have a look at this wonderful question based on P-N junction. The question says that the increase in width of depletion region in a P-N junction diode is due to. So we want to increase the width of depletion region. How to increase the width of depletion region? Option A, both forward and reverse bias can do that. Option B, increase in forward current. Option C, forward bias only. And option D, reverse bias only can increase the width of depletion region. Now, in order to mark the correct answer, we must be familiar with the concept of P-N junction. So let's go for a brief concept. So there are two types of semiconductor. This is P-type and this one is N-type. N-type semiconductor has excess electron as the charge carrier and P-type has excess holes. Now these two are electrically neutral. Although there are charge carriers present, but these two type of semiconductor are electrically neutral. Now we will do something. We will attach them. Boom! What do you think will happen? Well, some excess electron from the N side can flow into P side and fill up these holes. Wow! So these holes are filled. Now on N side, there is a lack of electron on this portion and there is excess of electron on the P side. Yes, so we have created a region known as depletion region. In depletion region, there are no excess charge carrier, but one side is negatively charged and another side is positively charged. This is our depletion region. So we have to talk about the width of this depletion region. How do we increase the width of this depletion region? That was the question. So we will do something. We will attach a battery and this is known as biasing. Now there are two types of biasing. One is forward biasing, one is reverse biasing. Look at the terminals of the battery. Tell me, which type of biasing did we do? Is this a forward biasing or a reverse biasing? Come on, you can tell that. See, the positive terminal of the battery is connected to the N-type semiconductor and negative terminal of the battery is connected to the P-type semiconductor. So this is known as reverse biasing. Alright? Okay. Now, what will happen to the depletion region due to this battery? What will happen to the depletion region? Whether it will increase or it will decrease. Come on, you can tell that. See, what can the positive terminal do? Positive terminal of the battery can attract electron. So, if we remove these electrons, we have the possibility of this depletion region to increase. And what can negative terminal do? Negative terminal can provide electron. So if some electrons are filled over here, we can see the depletion region can increase. So here's go the depletion region. Here go the depletion region. It increases. Yes. So this is how we increase the depletion region. Do the reverse biasing. All right. Okay. Now let's do something else. Let's remove the battery and this time we will connect the battery in reverse order. This is the forward biasing. Okay. Forward biasing. Positive terminal is connected to P-type semiconductor and negative terminal is connected to N-type semiconductor. Okay. Okay. Now, in this case, what will happen to depletion region? Will it increase or will it decrease? What do you think? Well, I think it will decrease. Why? Because positive terminal can absorb electrons. It can absorb electron. So, these electrons can be removed. And negative terminal can give electron. So, if negative terminal gives electron, there might be some electrons over here. Can you see them? Oh. Well, actually, negative terminal can repel the electrons. And if some electrons are repelled on this side, we can see in the N-type semiconductor, there are other electrons also. So those electrons can come and fill up this gap in the depletion region. Okay. This is why we decrease the depletion region like this. Okay. Okay. so we understand how the depletion region decreases. Alright. In order to increase the depletion region, we must do the reverse biasing. And if we want to decrease the depletion region, we do the forward biasing. Okay? Yes. So, we can go and mark option D as the right answer for this question. Let's have a look at this question based on current electricity. And this question is hard in our meter scale. Oh. So the question says, a resistance wire is connected to the left gap of the meter bridge. It balances 10 ohm resistance to the right gap at a point which divides the bridge wire in the ratio of 3:2. So this green wire is the bridge wire, okay? And this unknown wire of resistance, let's say X, is connected to the left side, and this 10 ohm is on the right side of the meter bridge. Now we have a balancing point. The reading of the galvanometer becomes 0 when we have the meter bridge wire divided in the ratio of 3:2. So this is the first line of the question. Now the second line says, if the length of the resistance wire is 1.5 meter, then the length of 1 ohm of the resistance wire is. So they say that this special wire, let's draw this special wire over here. This wire is of the length L is equals to 1.5 meter. And the resistance we don't know, let it be X. Now some portion of this wire has the resistance of 1 ohm. What is the length of that portion of the wire? This is the question. Did we get the question? Okay, yes. Now this question will be solved into two parts. So in the first part, we will balance out this meter bridge. We will find what is the value of X. In the second part, we will find out what is the length. Now we do the calculations for finding the X. Now we can see when the galvanometer reading is 0, when we have the balance point of this meter bridge, this meter bridge wire is divided in the ratio of 3:2. The ratio of length is the ratio of resistance on this meter bridge wire. Okay, so we can see 3/2. This must be equal to X/10. This is according to Wheatstone bridge principle. Okay, yes. From this we get the value of X. And X comes out to be 15 ohm. Congratulations for the first part of the question. Now we will move to the second part of the question. We have to find the length of 1 ohm portion of this wire. So 15 ohm resistance is there when the length of the wire is 1.5 meter. Okay, so for 1 ohm portion, the length should be 1.5 divided by 15 times 1. Okay, so this is giving us 1/10. Yes, so 1/10 meter should be the answer. 1/10 meter. Let's look at the option. Oh, we can see in option D, we have 1 into 10 raised to power minus 1. Yes, so that looks like the answer. So option D is the right answer for our question. So that was the last question of our discussion, and I hope you must have got a really good idea of what type of questions are being asked. I wish you all the luck, stay healthy, and keep learning. Bye-bye.